what we want to do to help us decide which mechanism is better, mechanism 1 or mechanism 2, we're going to calculate the delta H of the steps of mechanism 1 and compare them to the delta H of the steps of mechanism 2. We're going to focus on mechanism 1 first. We're going to calculate the delta H of the reaction for the steps of mechanism 1. And in step 1, the equation for the delta H of the reaction is the bond dissociation enthalpy for the bonds that are broken. In step 1, we're breaking a carbon-hydrogen bond. In your textbook, in table 4.2, which is going to be maybe not so hard to see here, you've got this table of a ton of bond dissociation enthalpies, and they give them to you in kilojoules per mole or kcals per mole, and we can use either one that we want. These are all for homolytic cleavage, which is exactly what we're looking at, and I already forgot what we're looking for, a carbon-hydrogen bond right down here, and the enthalpy for that in kilojoules per mole is 435. That's the bond that's broken, minus the bond that is formed, which is a carbon-chlorine bond in a CH3Cl. Here's a CH3Cl carbon-chlorine bond, and its enthalpy is 351. That works out to be 84 kilojoules per mole. Step 2 of that same mechanism, the delta H of the reaction, the bonds that are broken, which is the Cl2 bond, right here, 242, minus the bond that we form, HCl, from the table, it's right here, 431. That works out to be negative 189 kilojoules per mole. And overall, if we add this up to get the overall delta H of the reaction, it's going to add up to be negative 105 kilojoules per mole. That's really not going to be important, but we're going to put that in there anyways, just in case you're curious. The overall enthalpy of the reaction is just going to be the sum of these two, the sum of the enthalpy for step 1 and step 2. Now we're going to do the same thing for mechanism 2. Because what we want to be able to do is compare the steps of mechanism 1 to the steps of mechanism 2. In step 1, we're breaking a carbon-hydrogen bond in methane, a CH3H bond, 435, and we're making an HCl bond. And if we go to the table for that, an HCl bond is 431. That reaction is a delta H of 4 kilojoules per mole. In step 2 of mechanism 2, we break a chlorine-chlorine bond, which is 242, and we form a carbon-chlorine bond in a CH3Cl molecule, right here, 351. And that is negative 109 kilojoules per mole. And if we sum it up, just like we did in the last one, we end up with negative 105 kilojoules per mole overall, which is good. That makes sense because overall it's the same reaction. In order for us to determine which mechanism is preferred, we're going to look at the enthalpies of the individual steps and compare the enthalpies of the individual steps. Step 1, which is the first step of the reaction, for both of the mechanisms, it's an endothermic process. It's going to require an input of energy for it to proceed. But you can see step 1 of mechanism number 2 is much less endothermic than step 1 of mechanism 1. This step requires a whole lot less energy to proceed. This step requires a whole bunch. So if you have this system and you're putting energy in, by the time you get to 4 kilojoules per mole, mechanism 2 has already started and it's already going. And so because of that, because it's less endothermic, mechanism 2 is the one that's preferred. The whole entire mechanism overall. Mechanism 2 is preferred because its step 1 is much less endothermic. And the rest of the reaction, step 2, actually really doesn't matter. I suppose we didn't need to do that calculation, but those calculations are fun. So one more time, overall the reaction has the same delta H, negative 105. But if you look at just step 1, which is the first step that's going to happen, the step 1 for mechanism 2 that we proposed is going to happen much faster than step 1 of mechanism 1. So mechanism 2 is going to be the one that goes. Your study question. Will be, what is homolytic cleavage? So if I ask you to write me a reaction that shows the homolytic cleavage of the Cl2 molecule, you should be able to draw this out for me. And also, how do you use bond dissociation enthalpies to predict a mechanism? Now, I'm not going to ask you. You're years away from being able to come up with these, to propose potential mechanisms. But what I am going to ask you, what I am going to expect of you, is if I write out these two mechanisms right here and give you a table of bond dissociation energies, because I don't want you to memorize that. If I write these two out, or something like them, you should be able to do these calculations, look at the results, and know which one is going to be the preferred mechanism. Give yourself 3 minutes to summarize what's in this section. And on Monday, we are going to start with section 410 and 411. So we're really jumping around a lot in this chapter. We're going to do 410, 411, 412, 413, and 14. That should prepare you enough for Monday.